So question 9.3 asks us to suggest how these differences allow the mouse to have a higher metabolic rate than the horse. So we need to go back and look at our oxygen dissociation curve and see what that shows. So this isn't to do with the horse and the mouse, but it would show a similar pattern. This line here would be the horse, and this line here would be the mouse. So we can see that the mouse is shifted to the right of the horse. So what this shows is that the mouse's hemoglobin has a lower affinity for oxygen at a higher partial pressure, or at a fixed partial pressure, the mouse's hemoglobin is actually less saturated than the horse. So what this means is that the mouse is able to dissociate or release or unload more oxygen at a higher partial pressure, which can then be used for the metabolic reactions or respiration. So the oxygen is unloaded more readily or easily or quickly is fine at a higher partial pressure. They will reject the oxygen is loaded more readily, easily or quickly, or more oxygen is loaded. It's not to do with the oxygen being loaded, it's the fact that it is unloaded at a higher partial pressure because the mouse hemoglobin has a lower affinity, therefore that oxygen can then be used. So if we look at our mark scheme, hemoglobin is underlined. We must mention hemoglobin. We cannot just talk about the mouse and the horse. So the mouse hemoglobin has a lower affinity for oxygen, or at the same partial pressure, the hemoglobin is less saturated for the mouse, or at oxygen concentration found in the tissue, the mouse hemoglobin is less saturated. Then this means that more oxygen can be dissociated, or the oxygen can be dissociated or released more readily. It must be the idea that more is being unloaded, or the idea that it's more quickly or quicker. Therefore, the oxygen can then be used for metabolic reactions.